Welcome to today's class, and today we're going to be speaking about the Hess cycle. So, during our last lesson, we spoke about bond breaking, bond making, and we spoke about some definitions. So first, let's revise these two topics by working a couple of examples. Now, bond breaking, bond making, we said that bond breaking is always endothermic, bond breaking is always exothermic. So whenever you have a reaction, first you require energy to break the bonds, then you release energy when you make the bonds. In fact, we can see this, and we've discussed this in our previous lesson, in an energy diagram where you have your reactants. You first require energy to break the bonds, then you release energy, okay? And we said that these are the reactants, products, and your activation energy is the energy required to break the bonds. Now, okay, we can speak about bond breaking, bond making using an example that we've got here. So the enthalpy change for the following reaction, okay, the following reaction is hydrogen plus iodine to give 2HI is minus 9 kilojoules per mole. Use the information provided to find the energy in the HI bond. Now, if you want to try this on your own, feel free to stop the video here and continue once you are ready. Okay, so stop the video here and continue once you are ready. Now, this question really needs the knowledge of bond breaking, bond making, as we said, and we know that bond breaking is always endothermic. So hydrogen-hydrogen bond, this would be 435 kilojoules. Iodine bond, this is 151 kilojoules. And the two HI bonds is 2x. Because the HI is the bond making, therefore this value is minus 2x. During our last lesson, we also said that delta H of the reaction equals bond breaking plus bond making. Here we have minus 9 is equal to 435 plus 151 plus minus 2x, okay, which we can work out, make the x the subject of the formula, where x is equal to 298 kilojoules, okay, 298 kilojoules per mole of HI bonds. Okay, I would recommend that if you did not get this answer correct, please review the topic that we've done last week. Maybe look at the video provided for last week's lesson. Therefore, and if you got it right, we can then move on to the definitions. Okay, just a gentle reminder, breaking bonds is always endothermic. Making bonds is always exothermic. Okay, and then we can use that, to see what the value of the HI bond is going to be using algebra. Okay, very important. The equation that we use for this, for here, would be delta H is equal to bond breaking plus bond making. Bond making is always exothermic, therefore it's going to always have a negative sign. But it's important to have the plus bond making, okay? And then you put the negative sign for showing that it is an exothermic reaction. The definitions, we have two definitions. We did the definition of enthalpy of formation and enthalpy of combustion. Here, the enthalpy of formation is preparing 1 mole of product from its elements at STP, okay? Whereas the enthalpy of combustion is burning 1 mole of compound or element in excess air at STP. And the two important things here is that we are always either preparing 1 mole of product or we are burning 1 mole of substance, okay? We're never, ever dealing with working and doing more than 1 mole or less than 1 mole. It's always about 1 mole. So as an example, I would like you to try to find the enthalpy of, to write equations for the enthalpy of formation of aluminum oxide and aluminum. Again, if you would like to try it out yourselves first, please stop the video here and continue once you are comfortable with your answers. So, enthalpy of formation of aluminum oxide. So the elements are aluminum and oxygen to give Al2O3. And when we balance it, we do get 4 aluminum, 3 oxygens, and 2 aluminum oxide. Now, it's important to note that this is not your final answer, because your final answer requires to have 1 mole of aluminum oxide, and here we have 2. Therefore, we will need to divide everything by 2, so this will get 2Al plus 3 on 2O2 to give Al2O3. On the other hand, for the combustion of aluminum, we can start with the same reaction, but this time round, we need 1 mole of aluminum rather than 1 mole of aluminum oxide. And this ends up having Al plus 3,4 on 2 to give 1/2 Al2O3, where we divided the original balanced equation by 4. Okay, we divided the original balanced equation by 4. So now we are going to speak about the Hess's law. And Hess's law states this: the heat of any reaction for a specific reaction is equal to the sum of the heats of reaction for any set of reactions which in sum are equivalent to the overall reaction. Now, I know we are repeating a lot heat of reaction, okay? So let's try and explain this in more simple terms. Prior to today's lesson, okay, last week, we spoke about bond breaking and bond making. Now, and we said that energy is stored in bonds, and if the energy is stored in the bonds, therefore, if you have any reactant to give any product, the route taken to go from the reactant to the product will not change the energy that is stored in the bonds. Therefore, any route that can take you from one reactant to a product will always have the same amount of energy. So Hess's law states that no matter what route you take to go from the reactant to the products, the heat of reaction must be the same. And therefore, we can now draw a Hess's cycle. So what do we need to do to draw a Hess's cycle? And I love to write a few steps so that we can try and do this the best possible way that we can. Okay, so today we're going to learn how to draw a Hess's cycle. Okay, and this is what's going to be important for you guys for today's lesson. Okay, so anything prior to this was revising what we've done last week. So if you have a problem with that material again, please do revise and please go and check. Okay, go and look at the video provided for the previous lesson. So drawing a Hess's cycle. So the first step to draw a Hess's cycle is note all the reactions given. A reaction doesn't have to be like what we've had before, for example, H2 plus I2 to give 2HI. If I give you something like delta H of formation of HI, that is a reaction on its own. Okay, why? Because delta HF means enthalpy of formation, and formation of HI will have to be from the elements. So that is a reaction on its own right. It might not be the reaction that you're most comfortable with and more used to, but it's a reaction on its own right. Okay, once you note all the reactions, write all the reactions in full. Okay, and again, what do I mean? If I have an enthalpy of formation of hydrogen iodide, then I write it as H2 plus I2 to give to HI. For example, delta HF HI, that's gonna be half H2 plus half I2 to give HI. So this is the reaction in full. This would be the reaction given in your question. Okay, that would be the reaction that you would need to note down. Once you have noted down all the reactions, balance all of the reactions together. And the last step would be draw the cycle and find out your unknown value. So, what do we mean here? So first and foremost, balance all of the reactions together. In a Hess cycle, it's important that if in one reaction you are producing 2 HI, all the other reactions must include 2 HI. Okay, we'll see this in the examples that we're going to be making and showing you throughout the next few minutes. After that, we're going to draw the cycle, the Hess cycle, and we're going to be using it to find out our unknown values. And we'll do this because we need to find the different routes that are available. And once we find the different routes, then we can compare them to each other because they should be equal in energy. So let's try the first example, okay? And the first example is going to be the reaction, the combustion of ammonia, but it is not delta HC because it's not going to be for 1 mole of ammonia. So that is something that we need to note down. Okay, so we have 3 reactions. The reactions are formation of water, and we've got the corresponding value. We have formation of ammonia, we have the corresponding value, and we have the reaction, the enthalpy change of the reaction that we need to find. So we have 3 reactions, and we are going to write all of them down. So delta HF H2O is going to be H2 plus half O2 to give H2O, and this value is minus 286 kilojoules per mole. We also have delta HF NH3, and this would be half N2 plus 3 on 2 H2 to give NH3. Remember, if you are not sure how you're writing the equations, again, look at last week's video, okay? But what we're doing is we first balance the equations, and we actually do them for 1 mole of ammonia. And this value is minus 46 kilojoules per mole. And then the last reaction is our unknown, and this was 4NH3 plus 3O2 to give 2N2 plus 6H2O. And I love to balance the equations here. So that's the waters. I'm going to mark all of these first. NH3, we're going to make sure that they are all coupled together. H2, O2, And last but not least, we've got the nitrogens. So in these three reactions, every single component is written twice. Now, we have 6 water, 6H2O in our reaction, so we will need to multiply that by 6. We have 4 NH3s. We'll need to multiply this by 4, and this should mean that everything is balanced. So let's write it down, let's write everything down, and we'll see what we're gonna have. So we're gonna have 6H2 plus 3O2 to give 6H2O. We have 2 and 2 plus 6H2 to give 4 NH3. Okay, and we're going to have 4 NH3 plus 3O2 to give 2 and 2 plus 6H2O. And the corresponding energies, this would be minus 286 times 6, and this is minus 46 times 4, okay? And this would be, or these would be the values that we're going to be dealing with from now on. Okay, let me rub off the dot from there. Okay, so this is something that is going to be our three equations. And again, we're going to use the same, we're going to make sure that everything is balanced out now. So we've got 6 hydrogens, or let's try to use the same colors. 2 nitrogens, 2 nitrogens. We have 3 oxygens, 3 oxygens. We have 6 hydrogens, 6 hydrogens. We have 6 waters and 6 waters. And we also have 4 NH3s and 4 NH3s. So now it's time to draw all of these in a cycle. Okay, it's time to draw all of these in a cycle. And I love starting with the reaction that I have as an unknown. So 4 NH3 plus 3O2 to give 2 and 2 plus 6H2O. And then I pick and say, listen, the nitrogen, there are 2 reactions to give off the nitrogen, the ammonia, apologies. So ammonia can react with oxygen, or it can be produced from nitrogen and hydrogen. So it can react with oxygen. And the second reaction where ammonia is involved is its preparation from, its preparation from 2 nitrogen plus 6 hydrogen. Now, this reaction and this reaction needs to be balanced. And to balance them, we will need to add 3 oxygen. Okay, to balance them, we will need to add 3 oxygen. For the water, okay, I have the 6H2O, and 6H2O is also prepared from 6 hydrogens and 3 oxygens. And to balance these 2 reactions, I will need the 2 nitrogen. Therefore, it's already balanced. Okay, and at this point, I can now draw a circle in the middle. Okay, the circle I will draw the arrows as showing on the reactions, and I will be able to analyze which reactions are gonna be clockwise and which reactions are gonna be in the anti-clockwise route. Apart from this, each reaction has an enthalpy change associated with it. So I can also try to write these values on the reaction. So this is the one we don't know. This is minus 286 times 6, and this is minus 46 times 4. Now, the reactions here we have 2 that are going on the clockwise direction, the red and the black, and the purple is going anti-clockwise. So we can then say that minus 46 times 4 plus x is equal to minus 286 times 6. Okay? And if we work it out, x is going to be equal to minus 1532 kilojoules. Okay? If we work it out, x will be equal to minus 1532 kilojoules. Now, I would recommend at this point to stop, rewind the video, okay? Let's go back to the start of this explanation and see it and watch it again. At that point, we have another question. I would highly recommend to stop and try it, okay? So first note down what reactions you're gonna have. Then write down all the reactions. Make sure that everything is balanced and draw the cycle. Okay, once you draw the cycle, try to find the value of the unknown reaction. In this case, it's going to be the reaction of CH4 with Cl2, the free radical substitution when CH4 reacts with Cl2. So, if you want to try that, stop the video and then continue after you're comfortable with your answer. Okay, stop the video and then continue after you're comfortable with your answer. Okay, now, so let's start. The reactions we've got here are the enthalpy of formation of CH4, enthalpy of formation of CH3Cl, enthalpy of formation of HCl, and the actual reaction that's been given, okay, which is the CH4 plus Cl2 to give CH3Cl plus HCl. So we will first write enthalpy of formation of CH4, and this with carbon plus 2 hydrogens to give CH4, and this is minus 74.8 kilojoules per mole. We also have delta enthalpy of formation of CH3Cl, and this is carbon plus 3 on 2 H2 plus half Cl2 to give CH3Cl, okay? And this is minus 134.5 kilojoules per mole. We also have the enthalpy of formation of HCl, and this is half H2 plus half Cl2 to give HCl, and this is minus 92.3 kilojoules per mole. And we have the last reaction given, that is CH4 plus Cl2 to give CH3Cl plus HCl. Okay, so you write down all of the reactions. Now, once you write down all the reactions, you try and make sure that everything is, or all the components are present, okay, and see if they are balanced. If they are not balanced, balance them. So one CH4, there's one CH4, okay, carbon and carbon, CH3Cl, CH3Cl, HCl, HCl, and now here it was a little bit tricky. The Cl2, you have Cl2 here, and you have half a Cl2 there and half a Cl2 there. So there are ways how to do them, how to get to one Cl2 and one Cl2. Same for the hydrogens, 2H2, and you have 3 on 2H2 and half H2 here. When this happens, try and draw the cycle with what you've got and see if they actually balance out. But if the carbons are balanced, the CH4s are balanced, and the chloromethanes are balanced, it's very possibly that everything else will be balanced as well. So try to draw the cycle and see what happens. So at this point, okay, we start with CH4 plus Cl2 to give CH3Cl. plus HCl, okay? And we know that CH4, there's also the formation of CH4, and that formation would be carbon plus 2 hydrogens, okay? And here we can also add the chlorine, so we can balance that side with all of this, plus Cl2, and we now have two sides that are balanced. We can then see what's available on the other reactions, okay, on the third route. And this, in fact, will give CH3Cl and HCl, and they are perfect. Because the formation of CH3Cl and HCl will require 1 mole of carbon, 2 moles of hydrogen, and 1 mole of Cl2. And you can see that even though there are two products that require hydrogen and that require Cl, together they will amount, okay, to 2H2 and 1 Cl2. I will then draw the circle, okay, and we can see where the arrows are pointing, and we have two reactions pointing to the clockwise direction and one reaction pointing to the anti-clockwise direction. And we can start by putting in the values of each reaction. So our unknown first, formation of methane is minus 74.8, formation of chloromethane is minus 134.5, and formation of HCl is minus 92.3. Because these two items, okay, the two reactions are pretty much on the same route, on the same pathway, we can add them together. And here we will have then x minus 74.8 is equal to minus 134.5 minus 92.3, where x is equal to minus 152 kilojoules. Now, so what do we do from here? We have finished the first few examples. And now, underneath the link of this video, you will also find a worksheet. And you can start working a few questions from this worksheet. I would highly recommend to try them all. But if you have a problem, maybe you haven't understood what we're doing or why we're doing it, okay? Then I would highly recommend that you contact me, okay, with any queries that you might have. If you do not have any queries, please try the questions below and we'll go through them together as a class during our next lesson. If we are still going to be online, then I will recommend that you send me a photo of your work and I will be able to review it and tell you whether you achieved the correct answers with the correct working, and if not, I will tell you where to improve. So, a quick summary for what we've done today. We started off with a revision of last lesson's work, which was the bond breaking, bond making, and the definitions of the enthalpy of formation and enthalpy of combustion. Then we explained what Hess's law is, that no matter what route is taken to go from the reactant to the product, the energy will be the same, because the energy is stored in the bonds, and the bonds do not change. And then I went on to explain how to draw a Hess's cycle, and we've worked two examples, okay? And we've worked two examples. A quick recap on how to draw the Hess's cycle. First, note all the reactions given, then write all the reactions in full, okay? Because sometimes the reactions are given as definitions, enthalpy of formation, enthalpy of combustion, and there are other definitions we have not yet covered, okay? But for now, we're gonna be dealing only with enthalpy of formations and enthalpy of combustions. Balance all of the reactions together. Make sure that if you have 2 moles of a substance, okay, in one reaction, the other reactions will add up to 2 moles of that substance as well. And then draw the Hess's cycle, draw the cycle, and find the value for the unknown value, okay? There is always one value which is unknown. Then you can find it. If you do have any queries, please do not hesitate to contact me. Otherwise, I will see you next week with a new video, and we can continue working a few examples of Hess's cycles, and then we will work a different cycle called the Born-Haber cycle, which is one particular example where we will be able to use a Hess's cycle in real life, okay, in a laboratory. Thank you for your attention, and I will see you next week.